do que estava fazendo na última aula. Então, vamos recapitular complexos. Não lembro se a gente fez diretamente, mas a gente perdeu um tempo procurando o splitting, então vamos fazer complexos splits, ou split complexes. Por já não sei. Bom, vou continuar assim um tempo, alguém me grita que devo virar para inglês. Então, complexos escindidos, em espanhol a palavra é split complex. Split exact. Que em K espaços vetoriais isso sempre acontece, ou seja, vamos começar com K espaços vetoriais. C é um complexo de K espaços vetoriais. Acho que a nossa anotação da gente é assim, com K um corpo. K is a field. So then, what we have is just vector spaces, and we have this map from CK plus 1 to CK, oops, it's a bad idea, Cn plus 1, Cn, Cn minus 1, which is this differential. And the kernel of this guy is Z, Zn. By definition, and the co-kernel of this map I write it like this, is that quotient. Now, this is a sequence of vector spaces. There's always a splitting, so you can always find a subspace on this Cn, which is complementary to this Zn, and this is what we were calling last time, just like the book, Zn plus this B prime n. And the reason we're using this letter B is that, well, the image of this D inside of Cn is Bn. So let's use indices here to distinguish that guy from that guy. This is inside of Cn. That was the definition of the boundaries. And the whole point is that, well, this quotient here is isomorphic to Bn plus 1. Is that clear why? This is clear why this size, well, by this definition, shift everything by 1, and well, you'll see that Bn plus 1 is a subspace here that is the image of Dn plus 2. Is this isomorphism here clear? Or can anyone prove me why these are isomorphic? Why this Bn, oh shoot, yeah, this was a bad notation there. I'm not claiming that the sum is isomorphic to that. I'm claiming that this guy here is isomorphic to this. So only this, B prime n is isomorphic to Bn plus 1, and this is inside of Cn plus 1. Well, from Cn plus 1 to Cn, there's a map, which is this Dn plus 1. Its image, if this Bn is Bn. And what I'm asking is, why this isomorphic? Is this isomorphism? Okay. Sorry? Yes. Oh, okay. Go ahead. Okay, good. Yeah, but also, but I think in general, right? So if I have a linear map from a vector space to another vector space, then if I kill the kernel, then, so I have a map, which is this dn, and it factors through the quotient by the kernel of that map. Right? So here, I have this Cn divided by Zn, like this, and Zn is the kernel of this map. So again, by definition, the Zn goes to 0 here. So this means that this arrow here exists, making this diagram commutative. That's the fact that Zn is in the kernel of this map. Okay, so now, so that's, well, I guess here, the map from here to here. So now again, why from there I can see this Bn plus 1 there. Oops, sorry. I think I'm shifting, I'm thinking in cohomology versus homology. And someone should have complained. Someone should have complained here. That one would never be there. So the image of this map is Bn minus 1 here, not Bn plus 1. Sorry, I'm used to seeing arrows in this direction and the maps, these increase in degree. And here is this. Oops. Here no, here is same. So this space here, the image of D is isomorphic to that space. And the image of D, by definition, is Bn minus 1 inside of Cn minus 1. Yeah, I'm sorry. I should probably start writing the arrows in the other direction when it's homology instead of cohomology. But yeah, so we have this isomorphism between B prime n and Bn minus 1, which is Cn minus 1, which is inside of Cn minus 1. So in particular, B prime n plus 1, therefore, is isomorphic to Bn. Okay, so the other thing we did is we looked at Zn and inside, well, the same splitting. We looked at Bn, which is inside of Zn. Right, the image of D, that was the fact that this was a complex, that the image of Dn plus 1 is inside of the kernel of Dn. The composition of these two guys was 0. And then the quotient of this, whatever this is Zn mod Bn, comes to 0. And again, this is split. So Zn can be written as, well, actually, Bn plus this space, whenever I choose any splitting here. But this space is the kernel of D modulo the image of D, and this was our definition of Hn. That was our definition of the n homology group. Okay? So what I see is that I have this guy Cn, and I can project this guy to B prime n. This B prime n, so I have maps this way. I have maps to Zn, okay, which are the projections. So we have a canonical map from Zn to Cn, but by choosing this splitting here, we've gained a map this way, which is the projection in one of the summons. So I have a map from Cn to Zn. And I have a map from Zn, which I can project to Bn now. Again, from Zn from Vn, I have a map, a canonical map to Zn. This is canonically included here by definition. But by choosing this splitting on the homology, I've gained this map for free, which is this projection in one of the summates. So the composition of these two maps is a map from Cn mapping to Bn. But Bn is isomorphic to B prime n plus 1. And B prime n plus 1 is inside of Cn plus 1. It's one of the splittings that we've chosen for n plus 1 here. Right? So let's rewrite this equation here as Cn plus 1, which is isomorphic to Zn plus 1 plus B prime n plus 1. So this guy here is inside Cn plus 1. And this composition here, I'm going to call this guy S or Sn, it doesn't matter. By choosing these splittings, we've gained those guys. And these splittings exist only because I have short exact sequence of vector spaces. So for any subvector space of a vector space, I can choose a complementary subspace. At no point I've used finite dimensionality there. Okay, so we have these maps. So what are these maps? Notice that if I look at D composed with S, I don't want to keep track of the indices because I'm sure I'm going to screw it up like I did here. So let's take the indices wherever these guys are defined. Namely, I'm going to take S, and then I'm going to take D. D is going to go back this way to Cn. So what this S was? Well, this S was first project to this kernel, to Zn, and then project to Bn from Zn, and then take D of that. So Bn is the same thing as the boundaries B prime n plus 1, and then take D, which goes back here. So this thing here, what it does is just the projection, right? So I'm looking at first projecting to Zn, and then projecting to this, back to Bn. So in this splitting here, that composition, ds, is just the projection from Cn to B prime n. So this is a map from Cn to Cn, but it actually factors through B prime n. And if we do this the other way around, S composed with D, then, well, same thing. So if I do D first from, I guess I'll do this from Cn plus 1, then you map by D to an element in Cn, and then you apply S again and you go back here. But where do you land? Well, the first guy, D, is just a projection to B. By definition, this D, the image of D, is in Bn. So that would be the projection from to Bn, like this. Okay. So what you see is that the kernel, well, first of all, and that was the definition, is that if you do dsd, then this is the same thing as just applying D. So if I start from Cn plus 1, and I do D, I do S again, and then I do D again, this is the same thing as doing D. Of course, if I was in the kernel in Zn plus 1, this would be killed, because the first D kills it. But the whole point is that it gets killed on both sides. And if I restrict both sides to the boundaries, it's just the identity, because those were the projections. So this is the idempotency of a projection. And this is the definition of a splitting. So definition, a splitting is a collection of maps Sn from Cn to Cn plus 1, such that D is ds. And what we checked is that every complex on K vector spaces admits a splitting. It's not true that this exists. So now a complex is split exact if it has a splitting and is exact. When you have a splitting like this, let's look at these two projections. If you look at the kernel of one, you're going to land in Zn. And if you look at the kernel of the other one, so the intersection of the kernels here is the homology. So let me write this in a different way. The kernel of ds plus sd is the homology. And put the indices so that it makes sense. So I guess Sn lands in Cn plus 1. So this guy goes back to Cn. And then here I want to put an n plus 1. And then, no, probably here I want to put n. And here n minus 1. This is an isomorphism. Moreover, what we checked last time is this. So that's this S are maps from Cn to Cn plus 1. We can relax it a little bit. And we can do this for two different complexes. So let's say that we have two complexes. So we have a Cn plus 1 mapping to Cn, mapping to Cn minus 1 as discontinuous. And it comes from whatever. And I have a dn plus 1 mapping to dn, mapping to dn minus 1, and this continues. And choose any maps in this direction. So this is Sn, and this is Sn plus 1, minus 1. Any linear maps. So this is D. This is D on the complex C, and this is D on the complex D. This sum here, ds plus sd, is a map from Cn to Cn, is a map from C to D. Again, I need to put indices, and I don't want to put them. These are these indices. So this composition this way plus this composition this way, that's this map here. So let's put a name to that map. Let's say that this is F. And this is a map of complexes. So Fn commutes with D. F commutes with D. Indeed, F composed with ds plus, oops, no. F composed with D is F, oh shoot, ds plus sd composed with D, which is dsd, because d squared is equal to 0 here, and df is D composed with ds plus sd, and d squared is equal to 0. So this is the D in the complex C, and this is the D in the complex D. So these are two different differentials, this one and that one, but both of them are equal, squared to 0, so this is dsd as well. So these two are equal. That means that this map F, if whenever I choose any kind of splittings, I get a map from the complex C to the complex D, which is a map of complexes for any maps Sn. Okay, and the point is that if I have two different maps of complexes, that they differ by a map of this form, they induce the same mapping homology. So a bunch of definitions. Definition: F from C to D is null homotopic. A map of complexes is null homotopic if there exists S such that F is equal to ds plus sd. So a map of this form is going to be called null homotopic. And two maps of complexes are called homotopic if they differ by a null homotopic map. Say F and G from C to D are called homotopic if there exists a homotopy, or well, if F minus G is null homotopic. Or this is called the S that realize that map being null homotopic. Null homotopic means there exists such an S, such a ds plus sd is F minus G. That S is called the chain homotopy from G to F, or from F to G in that case. All right. So we may have to need homework. Okay. The only theorem we care about in this area is this theorem, or lemma perhaps. If F is homotopic to G, so this means homotopic, then F star is equal to G star, and this is the map inducing homology. So two maps that differ by a null homotopic map are not seen in homology. Homology does not distinguish two maps if they only differ by homotopy. So let's prove this. This is very simple. So first of all, I don't remember if I mean I mentioned this, that it was trivial, but I think I didn't define these F stars and G star. So first, that definition, we have these maps Cn plus 1, D, Cn, Cn minus 1. And then I have this map F to Dn. Here I have some F, and here I have some F. So now, let's choose an element in the homology Cn. So let's choose some alpha in Hn of C. Then alpha can be realized by an element in Zn. This guy here was Zn divided by Dn. So let's say that alpha is the class of some A, where A is in Zn. So that's where my alpha is, and A is in Zn realizes that class. So then I'll define F star of alpha as the class of F of A. And I need to check that this thing is well defined everywhere, that it doesn't depend on all the choices. So the only choice here is A, and I can change it by an element from Bn. So I can change my A by some other A prime, which is A plus an element in Bn. So this is some D of B, and now B is in Cn plus 1. But so what I want to check is that the class of FA in homology is equal to the class of FA prime. But the class of FA prime is the class of FA plus FDB. And, well, this is the class of FA plus the class of DFB. And here's because F is a map of complexes, so taking D of something and then F is the same as taking F and then D. And if I do F and then D, this is D of something, which is 0. Okay, so that's this map F star. Now, I may have two maps that are honestly different. F and G can be different maps. Namely, DS plus SD may be the non-zero, a non-zero complex map, or map of complexes. However, the claim is that even though these maps might be different, their difference is 0 in homology. So we need to check that. Okay, so let's grab an alpha here. Let's apply F, and let's apply G, and let's check that it's the same homology. Okay, so the claim here is that if I have some alpha, again, as here in Hn of C, then I want to check that F star of alpha is the same thing as G star of alpha. But then choose this A that realizes that alpha in the same way. This was the class of FA. And this is the class of GA. We've checked that this doesn't depend on the choices that we've made. And the difference between F and G is of this form, is DS plus SD for some S. Okay? So FA minus GA, this class, which is what I want to check that is 0, did I get it right? Yeah, it's F minus G. So this is the same thing as the class of DS plus SD applied to A. Now, A was in Zn, so SDA is 0. And I'm left with the class of DSA, which is 0 because it's D of something. Okay. All right, so having homotopies between different maps makes the map essentially 0 in homology. So we want to kill homotopies somehow, to not have this, this apparent extra symmetry that is not really seen in homology. Yes? No. Oh, that's a very good question. So, no. So if you have two map of complexes that induce the same map in homology, it's not necessarily true that there exists a chain homotopy between one and the other. That's yeah, that's a very good question. Yes. All right. Any other question along those lines? Actually, it probably is non-trivial to come up with an easy example of that. Yes, so the whole theory is cooked up in such a way that, well, you have this category of complexes that is quite complicated, but we only care about homology somehow. We want to abstract what is the thing that homology is measuring. And you'd say, okay, so then let's consider two complexes the same if they have the same homology. That's very strong, and then that's hard to do. So then let's consider two complexes the same if whenever you have a map of complexes from one to the other one, the homology induces an isomorphism of homology. That's hard to do. And this is one of the first steps into doing that. So I guess the upshot is, which we're not going to do this now, but people that do geometry, upshot, is this, is I would want to consider a category of chain complexes, something like this. Chain of R or whatever, complexes. But I want to do this following. Whenever I have some F, which is a map between C and D, such that this is an isomorphism, then I want to declare F to be an isomorphism. So that would be something like considering the class of complexes modulo those complexes that are quasi-isomorphic. This is stronger than saying modulo those complexes that have the same homology, because I am requiring that F exists to start with. This is a phenomenon that is very common in differential geometry. You look at vector bundles between two varieties, and then to find that you have two bundles, and you have a map between one and the other one, to find that those bundles are isomorphic, you need to check at each fiber. That's very simple. Check that whatever map you have restricts to each point is an isomorphism, and that's it. But the problem is to start already with a map, which is the hard part. So this would have been very different if I said I want to consider the category of complexes modulo declaring two of them isomorphic if they have the same homology. So I'm requiring that this F exists. So how do I do this? Okay. So if I just add explicitly an inverse for each such map, I'll run into a lot of trouble. And that we cannot do. So the first thing we're going to do is first get rid of, consider two maps to be the same if they are homotopic. And this causes another set of trouble, but that set of trouble is manageable. So that's what we'll do now. Well, probably not now. I want to say some other thing. I want to give some examples before. So let's remember the cone, because that's the easiest of the examples. So let's look at the identity map from a complex to itself. And let's look at the cone of that map. Okay, so this guy was a complex that, remember, we took this guy, we shifted it by -1. And, well, actually, let's repeat the construction of the cone in general. Let's do this on the side to remember what this differential was. Okay, so remember that we had some B to C, some F, and then we declared the cone of F to be this B shifted by -1 plus C. And the differential here, well, the cone of F n plus 1 is B shifted by -1 n plus 1. So that's B n plus C n plus 1. So that's C n plus 1. Oops. And I want to map a differential from here to the cone of F n, which is Bn minus 1 Cn. And I clearly have a map here, which is the differential of B, and a map here, which is the differential of C. And I have a map from this to this, which is my F. And for some reason, the book decided to choose these signs here. This is not exactly what we would get from the convention that we had for the double complex of this. I've defined before this cone as the total complex of this as a double complex. And that signs would have a different, different expressions for the total of the double complex, but it's fine. These two complexes are the same, essentially. So that's the definition of the cone of a map. In particular, if I look at the cone of the identity, when I put F to be the identity, okay, I claim that this guy is split exact. Okay, so I want to find the splitting, and I want to check that it's exact. Well, any quick proof that the cone is, can anyone guess quickly why the cone is exact? I mean, the splitting is probably not, it's not hard to see either, but why would it be exact? Why is this complex something that has zero homology? Okay, so let's see that we expect this to be true already on the nose. Okay. And why is that? Well, we had, let's do this in general for this. When we constructed this guy here, it came with natural maps of complexes from C to this guy. So the map from Cn to the cone of Fn that sends Cn to this component 0 here is a map of complexes. And the map from the cone of F to B shifted by -1, that is the projection to Bn minus 1, it's also a map of complexes. So we had this. We had a map from the cone of F to B shifted by -1 and to C, from C, I'm sorry. And this was a short exact sequence of complexes. This is something we had. And moreover, for any short exact sequence of complexes, we constructed a long exact sequence in homology. So we constructed this. From the nth plus 1 homology of C to the nth plus 1 homology of the cone of F to the n plus 1 homology of B shifted by -1. And we constructed this explicitly, this connecting homomorphism to the nth homology of C. And then to the, well, n homology. Let's write something. I think I always get this wrong on where should I start. So instead of continuing that way, let's start here from the nth plus 2 homology of B shifted by -1. So forth. And this is another. So those are the connecting homomorphisms. Now, this complex here is just the complex B that I just shifted everything by -1. So it's not surprising, it shouldn't be surprising to you that this, the nth plus 1 homology of this complex is the same thing as the nth homology of the complex B. Okay? And this is the nth homology of the complex C. And here, this is the n plus 1 homology of the complex B, and this is the n plus 1 homology of the complex C. So how does this look here? So I'm going to make a few claims here. I'm going to claim that this is the map F. So I claim that this del, this is a map from the nth homology of B to the nth homology of C. And we have such a map. We started with F, which is a map of complexes from B to C. So I claim that this thing here is F star in degree n. And this thing here is F star in degree n plus 1. I'll prove this in a second, but let's see how that looks here for the cone of the identity. So the identity certainly induces the identity mapping homology. Okay? So for the cone of the identity, where B is C, that sequence there looks as follows. It looks like hn plus 2, well, no, I'm sorry, hn plus 1 of the complex B, which is just C, to hn plus 1 of the complex C. And this obviously has to be an isomorphism because it's just the identity star. And this goes to hn plus 1 of the cone of F. And this goes to hn plus 1 of hn of B to hn of C. And again, these are isomorphic because that's the identity. And this sequence is exact. This is a long exact sequence. So if these two are isomorphic, this has to be 0. Because if these two are isomorphic, this guy has to be 0. Okay? In other words, the kernel of this map is the image of this map. Therefore, this map here is 0. And here, the kernel of this map has to be the image of this map. Therefore, this map here is 0. And that forces the whole group here to be 0 because the kernel of this map is the image of this map. Okay, so we expect that the cone of the identity map is trivial. It's trivial in homology. All of the homologies of a cone has to be trivial. I haven't used at all that this was the identity, so anything that is invertible would have given me the same thing. I've only used that these are isomorphism. So the cone of any map that is an isomorphism in homology should be trivial in homology. Okay, so how do we prove either that more general statement or just for the identity, the cone of the identity? So the cone of the identity, I think we can immediately show that is split, and that the splitting induces that, that triviality and homology for the cone. Okay, so what I want is look at this map, and I want to construct explicitly some splittings. Okay? So what is the splitting? So we would want a map from the cone of the identity n to the cone of the identity n plus 1. And this thing here, by definition, this is C, well, shifted by minus 1 plus C n, which is C n minus 1 plus C. And I want a map from there to this guy with n plus 1. So that's a Cn plus, oh, sorry, this is Cn. Here's a Cn plus 1. And there's only one map that I can think of. So there's only one map that I can choose from this space to that space. And that map would send A, B to, well, just B here, 0 here. And probably I need to put a minus in that B. I don't care. Okay, there's no other map that I can think of between these spaces. Okay, I claim that this is a splitting. So let's compute what is SD and what is DS. Okay? So if I start like this, I apply S, and then I apply D. And then, but D is on the complex. I need to remember that. Okay, so we have the differential in that last board there. So, okay, so I grab A and B, I apply S, and now I want to apply D. D lands in Cn minus 1 plus Cn, which is where I started. So what do? I grab AB, S sends it to B0. Now I need to look at D of this thing. Well, D, I read it from that border there, will have two components. This guy would send to 0 in Cn, so it doesn't matter. But the differential of this guy would land in both of them. Okay? So from Cn to Cn minus 1, I would take a dB. And I reserve the right of getting all of the signs wrong. But if I chosen this sign to be a plus, this would be a minus because of that, that thing there. Actually, I'm going to change this for a minus so that this becomes a plus, but that's minor at this point. But then there's another map, which is from Cn to Cn, which is the map F that we chose. That was the identity. And then again, I have a minus, so I need to put a minus. So that's ds. How about sd? Okay. So if I start with d first, right? So I want to compute d, and that d is going to land in c n minus 2 plus, because, well, this is from n goes to the cone of f n minus 1. Here I'm going to have an n minus 1. And again, what does d do to these two guys? Well, this guy goes here, and it goes to db. So I'm going to get here some db. And this a goes to both components. It takes a dA here with a minus sign, and then it takes a here with a minus sign. So that's what I've gotten here. And now I want to take s. So if I apply s, well, I read it from here. What I'm doing is taking the second component and putting it first. And I get db minus a, 0. Is that right? Or did I do something wrong? It looks okay? Well, hopefully it's okay. Okay. So now what I want to check is that what is ds plus sd of AB? So, well, I read it here. ds plus sd. Well, I got AB, I mapped it to this, and then I mapped it to this. So if I sum these two guys, I'm going to kill the dB, and I'm going to be left out with minus A on the first component, and with minus B on the second component. Which is minus the identity, which is minus the original map that I have. So the identity, well, for this splitting, what I'm getting is that minus the identity is null homotopic. So that means that minus the identity induces a trivial homology map, which means the identity induces a trivial homology map. If I wanted to get that identity to be homotopic, then change the signs here. So change this, choose this splitting to be minus b, so that this becomes plus, this becomes plus. Now here you would choose, this is fine because this is d, there's no change here. But then on the splitting, you're going to have minus here and a plus here, and you're going to get a plus and a plus here, and then plus identity. So this explicitly shows that the identity is null homotopic, and if it's null homotopic, we've already checked that it induces a zero mapping homology. So not only is split, but it's exact. Oh, well, no, I haven't. I've proven with this that the complex is exact. And now I need to check that it's split. I need to check that these S are actually splittings, because I gave a definition, a proper definition of splitting. So I need to check that dsd is equal to d. And we can take either of these expressions we have. So I have S, well, no, I want to take this. I want to take D, then S, and now I need to take D again. And, well, it sends 0 to 0 in the second component. So that's not much of a problem. But it sends the first one to D on the first one. And then d square of B is 0. And then I have a D of A. And in the second component, this D, what it did is it applied the identity map to this guy. So here, oops, what did I do? DS. I want to apply D to this. And it gives me D there. DA. Is it a splitting? Should be. What? Why am I not seeing? Oh, that's fine. Yeah. So I get DA, and then from the identity map on the other side, I see the DB. And then I also have the A. And that's actually what the differential of this object is. The differential of this, well, probably I got the signs wrong again because of the minuses. But the differential of this object is dB in here. And then the differential of A is dA on the first component and A on the second component. This is the identity. So that's fine. So we get this, that this is a split. OK, so the cone of the identity map is a split exact complex. And this is a canonical example of a complex that is, well, that is exact. It's a split exact complex. All right, so that's what we're going to use. We're going to, let's prove our original intuition coming from here, that this is true, that the connecting homomorphism for this short exact sequence coming from the cone is actually the map that I started with. So let's write that as a theorem. So if I have F, a map of complexes, then F star is the connecting homomorphism of the long exact sequence coming from this. So what this is saying is that the morphisms in homology that come from, that are induced from actual morphisms of complexes, they always fit in a long exact sequence. That's, I mean, though it's trivial, that's a deep statement. So if I have a morphism of homology of complexes, an arbitrary morphism, well, probably it's not of this form. But if I actually have a morphism that comes from a morphism at the level of complexes, then I can put it in a long exact sequence. And once I do this, then if I understand the cone, so what I want to understand is this map F and what it does in homology. If I understand any two of these guys, I understand the third because of this long exact sequence. We've exploited this by saying, well, I understood that these two guys were isomorphic, therefore I've gotten that this was exact. But sometimes the cone is easier to understand than one of the two. And since I have this long exact sequence, I can infer the third one by understanding the other two. Actually, the cone is known as the cone because it actually represents homologically what the cone of a map is in topology. I don't want to talk about algebraic topology, so you're going to do this eventually. No, the cone of the identity map of the sphere is, again, something that is trivial. It's null homotopic. The sphere is not null homotopic. I just proven. So there's a different thing of looking at the cone of something than the cone of the map of something. So if you look at the identity map of whatever thing is, and you take the cone of that, then you get something that is null homotopic. That is contractible. It's exact. Right? So we've proven that, and the sphere is not, so it cannot be. So actually what happens is that if you look at the sphere, you put another sphere, you take a map, and you look at the cone of that, what you're killing is all of the homotropy groups of the sphere by taking the cone of that map. Yeah, I didn't want to talk about algebraic topology, so I'm not going to start drawing things, but that's a nice exercise. Just look at the sphere, take the identity, look at the cone of that, and check that that thing doesn't have homotropy groups. All right, so where am I? Yeah, I want to prove that statement. But we have an explicit form. We have an explicit description of what this delta is. Remember how did we compute this delta? Okay. Either there or here, it doesn't matter. So we have some homology, and we want to go to the homology n-1 of the next complex. And this was coming from this short exact sequence. So I'm going to grab some n here, some n here. Probably I want to do n plus 1. N plus 1, n plus 1, n plus 1. I'm going to grab a class in the n plus 1 homology of this, and I'm going to lift it by the map of the cone that I have. So the rule was always the same. If you want to look at what is the connecting homomorphism here, just lift this using the fact that this map is surjective, take D in here, and that's your class. Go it back to C. So we grab a class alpha in Hn plus 1 of B minus 1, which is Hn of B. And such an alpha is represented by A in Zn of the complex B. Alpha is the class of that guy. So that means that A is in particular in Bn. And since this map is surjective, I need to find something in the cone of F that maps to A. So what was this map? Well, the cone of F n plus 1 is B shifted by minus 1 n plus 1, which is Bn, plus C n minus 1, n plus 1. So I'm looking for an element here that represents that A that is in Bn. So it has to be A. Okay. So A0 maps by this map here to that A. And probably it was minus A0, but I don't care about signs. I'm going to get all signs wrong anyway, so I'm not going to care about signs during the whole lecture. OK, so A0 is the guy that I have here that maps to A here. So the next step was take D of that in this complex. So I need to take D of this guy here. So that is minus dA. So that's why probably I needed to choose minus A here and have that this map was minus A instead of A, but it doesn't matter. So minus dA A. This is the differential of that guy in, oops, no, that's not A, it's F of A. No, the map is not the identity. It's cone of F, not the cone of the identity. And there's a minus F. According to what our D was on this guy. So now the claim is that this is in the image of something coming from C now. Okay? So that's how we computed this guy. I'm looking for a class. I don't remember if I'm doing this from Hn plus 1 for this, and I want to land in Hn of F, of C. Okay? So, well, that's it. So this guy here is in the class of F. Okay. And this is the composition of all of this map is delta. And this guy here, by definition, is F of alpha, F star of alpha. Right? OK. So that proves that we can put any map on a long exact sequence. I still have a little time. So want to do today. Okay, I should mention one example that the book has, and then I'll move to these homotopy cases. So the one example that the book has is this. Let's look at z divided by z4, well, by 4z. Z divided by 4z. Z divided by 4z. This. So this is a complex in the category of Z modules, abelian groups, or it could be in the category of Z over 4Z modules. It doesn't matter. For both of them, let's look at them as just as abelian groups. And the map is multiplication by 2. So if I multiply by 2, and then I multiply by 2, it's multiplication by 4, so the composition is 0. So that's a good differential. Multiplication by 2 is squares to 0. So that's a good complex. It's never the support of this complex is the whole integer site. So there's no element, there's no ck that is 0. This is unbounded on both directions. And it's clear that the kernel of this map in here, well, this consists of the element 2 and the element 0. 0 times 2 is 0, and 2 times 2 is 4, which is 0. So that's the kernel of this map, which are the two even, the image of the even integers here. And that's also the image here, therefore. The image of the even integers is, by definition, the image of multiplication by 2. So this complex is exact. The homology of this complex is 0. Right? This happens at every spot. And this complex cannot be split exact. So why can it not be split exact? Well, let's go back to the notion of being exact and split exact. So I claim that if you have a complex and you have a splitting and your complex is exact, then you can express the identity of that complex as an unhomotopy. It's easy that if this is true, then your complex is split exact. The identity is split because we're assuming that we have a splitting, this S. And it's exact because this proves that the identity induces a zero homology, the zero mapping homology. And the identity always induces the identity mapping homology. So if the identity is 0, then it has to be that the homology is 0. The converse is also simple, that if you have a split exact complex, then you're going to find that this guy here is invertible. And once it's invertible, you can just normalize it to be the identity. So why this cannot happen here? If I choose a splitting such that this thing happens, then I would see that this guy here would have to be, well, if there exists a splitting. Oh, wait. So let's look at that situation of a split exact complex. So when we had that situation, then we had this two. We had an explicit splitting of the homology. For split complexes, we had exactly what we started today's lecture and we finished last lecture. We had this Cn being isomorphic to Zn plus, I think, whatever I called B prime Zn. And this thing here was a Bn minus 1. But we had a splitting of the module as a direct sum of 2. And this can never happen for Z over 4Z. The kernel is Z over 2. And it's not true that Z over 4 is isomorphic to Z over 2 which is Zn plus whatever is left, that has to be Z over 2. So what it is true is that we have this. We have this. Z over 2 maps to Z over 4. This is Zn, the kernel of the differential, inside of the full Cn. And the kernel is Z over 2. So this is true. But if we had a splitting, then this guy would be the direct sum of these two, which cannot be true. All right. So that's one example. So no, it's not true that every exact complex is split exact. That's an example of an exact complex which is not split exact. The cone of the identity is not only exact, but split exact. What else? Which other example I wanted to give before starting with this? Well, the thing of using the cone is that it will reduce understanding of quasi-isomorphic complexes by understanding split exact complexes. So if I had a map F, right? What we've gained by looking at this complex, the cone of F, is that we've gained this sequence where we had an Hn. So again, I have a map F of complexes from B to C. We've gained maps like this from Hn of B to Hn of C to Hn of the cone of F. Hn minus 1 of B to Hn minus 1 of C. These are these F stars. This is the F star. And what we've gained is that if I want to understand what happens when F, so I was after a theory that would allow me to replace complexes by the same complex if they are quasi-isomorphic. So if this F induces an isomorphism in homology, I wanted to declare this complex to be the same as this. So I'm after something like this. I want to understand things modulo up to homology. So if this is a quasi-isomorphism, then this is an isomorphism, and this is an isomorphism, and this becomes 0. But this complex is split exact. This cone is always admit splittings. Cones are split. I did it for the identity, but it's clear what the same splitting would work for arbitrary objects. So understanding quasi-isomorphisms by this trick of using the cone, which is the total complex of a double complex, allows me to understand them by studying split exact complexes. All right, so finally, we finish with something. So there's an extra issue, which is you cannot start declaring any homomorphism on a category to be an isomorphism. So in principle, I could say, well, suppose I have a map of complexes like this, and let's suppose that F induces an isomorphism of homology. So then, how do I localize? How do I declare these two objects to be isomorphic? Well, then I invent one. I say, well, there exists a morphism this way, some G, which I declare it to be F inverse. So this doesn't mean that there's a morphism of complexes. I want to identify two things that this map might not exist. So I can add it to the category. I say, well, for each F, there's such a map. And if you do such a thing, well, you start identifying things. For example, something that is non-zero and has 0 homology would become 0. So if you start identifying things that are non-zero with things that are 0, you run into problems. Because you want to compose things and you want to find that you have an identity. At some point, you're going to identify an identity with 0, and then everything becomes 0. So this is very similar to when you have a ring and you try to start inverting objects. You cannot invert anything. Your thing should not have 0 divisors. You should not have everything inside. So it's not that you grab an arbitrary subset of a ring and you declare, well, I'm going to invert it. So when you want to localize on a ring, you cannot localize arbitrarily. And the same thing happens for category. You cannot declare any morphism to be invertible by just adding an inverse to that. So that's what I want to start slowly showing. How do we invert, at least how do we get to invert quasi-isomorphisms? So the first step is this, is that, so definition, let's declare Kn, well, K. So I had a category which was chains, chain complexes of anything, chain complexes of R modules, chain complexes of whatever it is. I'm going to call it chains. And I'm going to look to another category, which is going to be K. And this K is going to have the same objects as this. So if you were looking at complexes of vector spaces, this would be complexes of vector spaces. Complex of R modules, this would be complexes of R modules. What are the morphisms, though? Here, the morphisms between two complexes were maps of complexes. Homes in chains were maps of complexes here. So here, the morphisms between two complexes would be the morphisms between two complexes, modulo, and equivalence relation. And the equivalence relation is I'm going to declare two morphisms here to be equivalent if there exists an homotopy equivalence between them. So there's a lot of things to say here. First of all, the homotopy equivalence is an equivalence relation so that I can divide by the equivalence relation. I want it to be a linear equivalence relation so that this thing is still a vector space. So let's start checking all of these things. Okay? So it's clear from, remember what the equivalence relation is f minus g is equal to sd plus ds. And that this thing exists. It's clear that if f is equivalent to g, then g is equivalent to f. Right? Just shift s to minus s, and this thing happens. So that's what's the name of that? Is being reflexive. And, well, I'm very much dyslexic with this. But f is also equivalent to f. That's also clear. Because if I put g is equal to 0, then I can put just, I'm sorry, if I put g is equal to f, then this side is 0, and I can just put s is equal to 0. So that also works. So the question is, why if f is equivalent to g, and g is equivalent to h, how do I make s such that f is equivalent to h? I don't want to do that. Yeah, so the easiest trick so exercise. Do that. If f is equivalent to g and g is equivalent to h, then prove that f is equivalent to h. It's not so bad. Moreover, this is compatible with compositions. So that says that these k are well defined. The kn's are well defined. Just homotopy equivalence classes of maps. What's also clear is that if you have something like this, so that gives me this, guys. But now I'm in trouble because I need to prove that I have to compose maps. So I want this to be a category. So I need to prove that if I have a map from C to D and from D to E, I mean, as map of complexes, I can compose them, and I just compose them on the nose. But if I only have the homotopy class of a complex, I need to check that I take representatives, I compose them, and that's a good composition. So if I have some F here and some G here, well, probably I'll just H here, then I would want to prove that the class of F composed with the class of H, and I define it to be the class of the composition, the homotopy class of the composition, I need to check that this thing is well defined. And then again, that's also a pain in the butt, but it's not so bad. The point is this, is that, let's do it like this. And then I have here some, if I have two maps here, and I have, so if I have something like this, and let's suppose that F is homotopic to G, then what you need to check is that H composed with F composed with G is homotopic to H, oops, with J, H composed with G, composed with J. That's not so bad. That's really not so bad. What it is you just use the same S. So you have this S for F and G, and now you compose and pre-compose both sides with J and H. So if I have this, let's pre-compose both sides with J and H. And now J and H commute with D. They're maps of complexes. So this would give you the what? Add and subtract, you're going to get some explicit splitting that would just be the homotopy between this and this map, the two different compositions. Okay, so what else? So that makes K into a category. Which is the homotopy category. And there's one thing that I actually want to do in detail. That's why I'm just rushing here. Category of chain complexes in whatever it is. And that category is additive. This is also not bad to see that if you have two homotopy class of maps, well, everything here was linear. This is a linear map, S's are linear maps. So everything here is linear. So clearly, the class, the homotopy class of F plus G is the sum. Well, I define it to be this way, and this is a well definition. This does not depend on the classes that I've chosen, on the representative of the classes that I've chosen. So it's clear that the homotopy class is, the homotopy category is an additive category. 0 is the additive unit, and the homotopy class of 0 I declare it to be 0. What's not so obvious, and it's not obvious at all, is that this guy is not abelian. Well, it's almost always not abelian. So K is almost always not abelian. And I've given many times this question. I don't know, apparently there are some books that are famous. I've given many times this question. I've always gotten in exams, and I've always gotten this example, which is a false example, as a counterexample. So the question is, why is the homotopy category not an abelian category? So this is going to be an example of a category where I know how to add objects. So remember, what was an abelian category? It's a category where I have this addition. It's an additive category where I have kernels and co-kernels, and then I had some extra condition that the kernel of a co-kernel is the same thing, well, that every monic is a kernel of a co-kernel of its co-kernel, and every surjection is the co-kernel of its kernel. Those are more subtle ones, but the issue here is that there's no kernels and co-kernels. And the question is why? And this is the non-example. So this is not a counterexample, but it shows the confusion. So let's look at the category of chain complexes on abelian groups, or whatever it is. just take the identity here. And take the identity here. Take any map there. It doesn't matter. So I claim that this is a map of complexes. So this complex is a different complex. Neither of these complexes is 0. And I'm taking a map of complexes. It is 0 goes to 0 here, which goes to 0 here. 0 goes to 0 here, which goes to 0 here. So this diagram commutes here, and this diagram certainly commutes here because anything goes to 0 this way and it goes to 0 this way. So that's a map of complexes. The kernel of this map is non-zero. So if I call this map F, the kernel of F. So what's the kernel? In the category of chain complexes is an abelian category. So it has kernels and co-kernels. So the kernel of F, what is this? Well, in here is the identity map. So nothing here is in the kernel. Oops. Probably I want to change this. Probably I want to change this to a different morphism. No, I don't want to take the identity, perhaps. Well, let's do the co-kernel, I guess, and that's it. Let's look at the co-kernel of this map. So the co-kernel of this guy, well, in here I have this modulo the image, which is everything. So I have nothing. And let's put degrees. Let's say that this is in degree 0, this is in degree 1, because these are homology complexes. So this modulo this, I still have the whole of Z. So the co-kernel of this, it looks like Z put in degree 1. So this is like this. Okay? So that's that co-kernel. And the differential of that thing is 0. So it's non-trivial. Okay, so let's try to choose a splitting here. I can put the identity here. And I can put 0 everywhere. And this map is 0, and this map is 0. So, well, this is 0 on this side, and this is the identity on this side. So this says that this identity is null homotopic. Well, F is null homotopic. So F is a map that has a non-trivial co-kernel, which is this. F is an honest map of complexes here. The co-kernel of F is certainly non-zero in the category of complexes. But F is 0 in the homotopy category. F is equal to 0 in K. Let's put names to these complexes. So this is the complex C, and this is the complex D. Yep, because F is homotopic to the 0 map. And the co-kernel of the 0 map is the whole thing. And the kernel of the 0 map is the whole thing. So the kernel of F, so let's look at the kernel of F in the category of chain complexes now. Well, the only thing where it could be non-zero is at this degree. And there is the identity, which is nothing, is 0. So the kernel of F is 0 in the category of chain complexes. But F is 0 in the category of K. So if I had a kernel, the kernel of F would be the whole thing. So in the category of K, the kernel of F is the kernel of 0. And the kernel of 0 has to be the whole complex, C. I have a 0 map. The kernel is all of the source. So either so is C 0 or not? Or where am I finding a contradiction or not? Okay. So let's review the picture. C is this complex, Z sitting in degree 0. D is this complex. If you look at this, D is what? It doesn't matter. This D is this complex. I have a map from C to D. I'm saying that this map has a non-trivial co-kernel. The co-kernel of this map is Z put in degree -1. The kernel of this map is 0. The co-kernel is non-trivial, the kernel is 0. The map itself becomes 0 in the category K. And why it becomes 0? Because the identity is homotopic to 0. Okay, so now if I had kernels and co-kernels in the category K, then the kernel of 0 should be the whole thing, should be C, which should be 0. And the co-kernel should be, well, this modulus 0, so it should be D. Can anyone tell me if there's a contradiction here? What it is? We have a few minutes to try to understand what's going on. So first of all, this is a situation that we've already been describing. C is a complex, it's just Z put in degree 0. D is a complex, it's the cone of the identity of C. So D is the complex that we've been talking about. It's the cone of the identity of C. And it's no wonder that we have this short exact sequence. C to D to C shifted by 1, by -1. So that's the same short exact sequence that we've seen before. And the map F is this. On the other hand, this guy is 0 in the homotopy category. This guy is exact, is split exact. So in the homotopy category, this thing is going to be 0. So it's no wonder that everything here is 0. So this is not giving me an example of the lack of kernels and co-kernels in the homotopy category, because in the homotopy category what I have is that, yes, the map becomes 0 because this guy is 0. So I have a map from something to 0, and the map is 0. This identity map is 0 in K. It's null homotopic, and it's because it's a map of something to 0. So the co-kernel is 0, and the kernel is 0. Well, I shouldn't say the co-kernel and the kernel. Kernel and co-kernels don't exist, but the map is 0. So let me tell you why kernels and co-kernels don't exist in this category, except if the category consists of all objects being split exact. So for example, for the homotopy category of chain complexes of vector spaces, that category is abelian, because it's just the category of complexes of vector spaces. It is abelian. Any complex is split exact. So there are kernels and there are co-kernels. But for other categories not, and this is a theorem that I don't think I'm going to be able to explain now. The most general theorem is this, is in an abelian category, well, I'm going to write it like this. In K, every monomorphism is split. So I need to describe what does it mean to be a split monomorphism and why that theorem is true. It's not so hard. So let me quickly tell you what yes. Sorry? That's correct. Yes, every split exact complex is going to become 0. Sorry? That's correct. Because what you have for split complexes, you have a map to the homology, and you have an honest map to the homology. And if on top of that the homology is 0, then you have an honest map to 0, and that's an isomorphism. But yeah. No, there's not. So there's no notion of kernel and co-kernel. That's where I want to get. So that's. I'm not sure. I don't know how to answer this because since we know that there are no objects like this, then yeah, I do not know how to answer this. The thing is that what happens when you start. So when you change the notion of morphisms in a category, you also change the notion of objects in the sense that some objects that weren't isomorphic, now they are isomorphic. Particularly in a narrative category, you have some objects that were non-zero, and now they are 0. So yeah, I'm not sure. So before we had a unique kernel, which was this object, and now that object might become might have become 0. I do not know. But let me just give you the quick idea of this. I'm sorry, I'm going to take just a couple of minutes. No, probably I'll do this. I'll start next time. Let me do this quickly. No, I'll do this next time. The whole point with this is just to use the cone of the map and check that find the splitting explicitly. I'll do this next time. I'll give you one more chance.